All right, let's start with questions from homework. So Tessa, 46.
I agree. Yes.
Okay.
What's that?
All right, so it says, in the theory of relativity, the mass of a particle with velocity v is given by this, where m naught is the mass of the particle at rest and c is the speed of light. What happens as the velocity approaches the speed of light from below? So oh, there you are. So what we're looking for here is the limit as v approaches c of this, right? And we'd say that like the mass is going to be that, right? Okay. Physics students, does anybody know what's going to happen here? Elena? Oh, well, be careful with what we mean. What do you mean by big? You mean mass, right? Not big.
Oh, yeah.
Because big would imply volume, I think, for most of us. Mass isn't necessarily the same as volume, right? Okay, so the mass gets too big. By too big, you mean?
I don't know.
Like
I remember doing this.
Infinite, right? Infinite. Yeah, so that is what should happen. So if you remember that from physics, that's right on. So one of the things we're going to look at here in the next section is we're going to start looking at algebraic properties of limits. So how can we evaluate these limits without using a table or a graph, which for this problem, when everything is kind of a constant, is maybe not so realistic. What we can do, though, for where we're at, is we can just kind of assign some values. So maybe I say, like, let m0 equal 1, let v equal 2. Oh, I'm sorry, v is our variable, right? And then maybe let's let c equal 2. And just let's type this into the calculator and kind of look at the limit as v, which will be our x, approaches 2. So again, I'm going to type this in. I'm going to use that fraction command to just make a little shortcut. Oops, and that was x squared. Okay. Yeah, all right. So if I hit graph here, and I look, so if I start tracing that, it appears that as I'm getting closer and closer to 2, we're getting bigger. The graph didn't really have enough grain for me to tell so much what was going on, so maybe I'll use like a little tabular thing. You know, as I'm getting closer and closer here, it's continuing to grow and grow and grow the closer and closer to 2 that I'm getting. You can kind of see that the closer I'm getting to 2, the more it's growing, right? Which looks to me like it's bombing on off to infinity, which matches what maybe some of us remember from our physics class, that at, you know, very fast speeds or very small masses, things get real weird real quick. But that's the idea, right? So that's how I would have done it if I remembered from my physics. I'd been like, oh, I know this is going to infinity. If not, I'm just going to assign these constants some values and just kind of do it the same way I would have in class, right? Now, ideally, like, you could have used the actual speed of light if you remembered that, like, what is it, 3.0 times 10 to the 8 meters per second, I think. I don't know, it's been a long time. But I think that's it, or 186,000 miles per hour, I think is the speed of light. There might be some change on some of those numbers, but I think that's ballpark. They're not miles per, maybe it's miles per second. I don't remember. It's, yeah, I think it's 3.0 times 10 to the 8, like, meters per second, I thought, but yeah, it's been a long time. Okay. But Tessa, does that?
Yeah.
Okay.
So, the answer is
Yeah, it's going to infinity. Yeah, which is weird, right?
it goes to infinity or approaches it?
You can say either. You can just say the limit as, you know, v approaches c from below,
Okay.
m goes to infinity or approaches infinity. Either is okay.
Thank you.
Yeah. Rita.
Can you never say
17. Sure. And you guys are okay with the way we just kind of talked about, we're just kind of talking about some of these. Some of them you're getting a lot of, you know, we'd get a lot of detail if it was algebraic, but to a great extent, a lot of the stuff we've done so far is just kind of like building some intuition out and like some ways to check our intuitions. So that's not really precise there. All right. So 17 says to sketch a graph, a possible graph of a function that satisfies the given conditions. So I'm going to pause on the limits here, and I'm going to start by just writing down like f of 3 equals 3. So I know like 3 over and 3 up. And f of negative 2 is equal to 1. So like I have that, right? I know those have to be points. Maybe they're connected to the function. Maybe they're not. We'll see. So let's see. We have f of 3 from the right is equal to 4. So that should be coming into here. That's 3, 4. Now, I don't know if that arrow should be pointing down or pointing up, so it doesn't really matter. Doesn't matter. Either would be acceptable. I just need to make sure I have that open circle at 3, 4 and the graph coming into it.
So like if it's like a limit like the circle's open.
Not necessarily, but because I know there's a point at 3, 3, and the limit as we approach 3 from the right is 4, I know that it can't be defined at both 3, 3 and 3, 4 and still be a function.
So if it wasn't defined at the 3, then
it could be closed.
It could be, so it's
It doesn't have to be, but it could be.
How would you know then?
I don't know that you would. I mean, if you had the right-hand limit was also equal to 4, you could make it either open or closed, and it would be fine. Anyways, let's continue on. So we also know the limit as we approach 3 from below is 2. So again, at 3, 2, I'm going to put an open circle. And then the graph goes into that. Again, doesn't matter if it's kind of pointing down or pointing up. Either would be okay. And then the last one, it says that the limit as x approaches -2 is 2. So again, 2, 2, I'm going to put an open circle because I already have a point with the x value 2. And here, you know, both sides have to go into it because I have the limit. So I know the left-hand limit and the right-hand limit both have to be the same. So both sides of the graph are going to go into that open circle, and then I can just kind of connect up what I wanted to do there. And this could be pointing down or pointing up. It doesn't matter. You know, whatever happens in between these two open circles doesn't matter. I mean, you could have go if you wanted to. I don't know why you would, but like, it's fine. I mean, you could just draw a straight line, a horizontal line across. That's fine. You know, what you couldn't do is do something like this where it stops being a function because you fail a vertical line test. But, you know, like, what really mattered would be, you know, would be those parts, and then the graph has to just kind of like connect in. However you want to connect it in between them is probably okay. Feel good?
Yeah, thank you.
Sure. Isabel?
Can you do number 27?
Sure. 27. And again, you guys are good with just like me talking through the rationale for some of these that are a little bit more like conceptual, right? There's not a lot to write down other than like what your answer looks like. It says, by graphing the function, yada, 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 and zooming in toward the point where the graph crosses the y-axis, estimate the value of the limit as x approaches 0 of f of x. Okay. So we'll get our calculator out and just follow the directions. I'm going to do this. And I'm going to use the fraction command so I don't have to like muck around quite so much with you know, the parentheses there. So there's that. Isabel, you'd also want to make sure that your mode is in radians on something like this. Really, for this class, we're always going to be in radians mode. I'm just going to start with like a zoom trig. So I'll just format this for like a normal trig thing. So it looks like that's the spot right there. So let's just kind of zoom in towards that. So maybe we'll just go from like -0.1 to 0.1. And then it looks like from, that was between 1 and 2. It looked like that spot was. And maybe we'll scale it by halves there. And I'll just hit graph. Uh-oh, did I look at it wrong? Where did the... Oh, fiddlesticks. Ah, okay, so it's more like 1 or 1.5. Okay. All right. So we'll reset our window. We'll do 0 to 2, make sure we get it, and go by halves. Oops. Stop. Stop. You got like 1.5 or something, right?
Yeah.
Yeah, -1.5. Yeah, that's... Oops. All right, now, come on here, Kulik. There we go, -2. Just one quick sec, and I'd be happy to. So again, this is, you want me to go back to the y equals?
Yeah. How do you get the where the top and bottom?
The horizontal fraction bar, I press alpha and then y equals and pick the first option. That's a handy shortcut, as that vertical or horizontal fraction bar makes life way easier typing stuff into your calculator because you don't have to go parenthesis crazy to get stuff to go. But Isabel, when I look at that, zoomed in, it looks like negative 1.5 where we're crossing, right?
Yeah.
Part B says, check your answer by evaluating for values that approach 0. So I'll just go ahead and do vars, yvars, function, y1. And I'll just start by doing kind of the same thing. I'll do like negative 0.1, and then like negative 0.00 or 0.01. You know, and at this point, I'm pretty convinced we're going to negative 0.5. If I do the same thing from above, oops, you know, I'll just knock the negative sign off and just repeat the process. And I notice I'm getting the exact same thing, just with the, you know, so again, I'm pretty convinced that this is heading towards negative 0.5.
Wait, why did you put in like negative 0.1 again? Like,
So-
how did you know to choose that?
Well, it says the limit is approaching 0. So I have to check the limit from the left and from the right. So I pick something that's really close to it, but still below, and really close to still above.
Okay.
And I look as I'm getting closer to it, right? So I start with like 1 to 0.1 to 0.01, 0.001, and just kind of keep stepping closer and closer to 0.
Okay.
And you don't have to do it that way. Like the numbers you pick are arbitrary, but like I just change the decimal point because it just feels neat and clean and like systematic, and I like that. Talika?
Could you do number 11?
Sure. Screen cap. Okay, I just would like us to think a little bit about what we're supposed to be doing right now, and if we're watching stuff on our tablet, maybe stop. All right. So here it says sketch the graph of the function and use it to determine the values of a for which the limit of f of x fails to exist. So first step is I need to graph this thing. Can't really do that on my calculator because it's a piecewise function, right? So the way that we do this is we're going to do it by hand, but it's not difficult to do by hand because the pieces are pretty nice, easy to deal with pieces. So I'm going to start with the first piece. What type of function is 1 plus x? Yeah, it's a line, right? How many points do I need for a line? 2 would be appropriate. 3. I mean, 3 is fine. It's just one more than you need, right? So I'm going to need to pick x's that are less than negative 1. One of the x's I'm going to pick has to be negative 1 because I need to have the boundary. Now I know that negative 1 is not actually a member in the domain, but I need to have that because I'm going to put a little star next to it because that's where the function is going to change from like, I'm just have like an open circle there because I need to get right up next to it, and that happens at 0. And then maybe I'll pick another x, maybe negative 2. So I have like negative 1, 0, negative 2, negative 1. So like that's the first piece. Okay. Then I'll look at the next piece. What type of function is this? Quadratic, right? To graph a quadratic, how many points do I need? I need at least 3. One of them has to be the vertex. If my function is y equals x squared, what's the vertex? 0, 0, right? Okay. The other 2 x's I'm going to pick, surprise, surprise, are going to be the boundaries for the domain of that piece, negative 1 and positive 1. Now, positive 1 I notice is a strict inequality, so again, I'm going to put a star next to that one so I make sure when I draw it, I use an open circle there. Negative 1 squared is 1. Positive 1 squared is 1. So I have the point negative 1, 1, 0, 0, and then 1, 1. So I have like that. And then my last piece is another linear piece. Again, I'm going to start by, I need 2 points. I'm going to just pick 1, which is my boundary value, and then something else that's greater than 1. So that gives me what? 1 and then 0. So when I plug in, or I plot 1, 1, I notice that fills in my open circle there, right? And then I have 2, 0 is here. So this is my graph. Good with how I generated this? So now what it's asking me for is what are the values of A where this limit would fail to exist for this function. So basically what I'm going to be looking for here is a jump discontinuity. I need a situation where the graph from from the left end goes to one value and from the right end goes to a different value. The only place that happens is right here at -1. So we'd say like the limit as x approaches -1 of f of x does not exist. And you could say because the limit as x approaches -1 from the left of f of x is equal to 0, and the limit as x approaches -1 from the right of f of x is equal to 1. Does that feel okay there? So the tricky part was like, how do I graph this piecewise function? All you do is just graph the pieces. You just use what you knew from Algebra 2 to graph each piece separately on the same axes. You have to be careful with the open and closed circles at the boundaries, but that's kind of the hardest part. But once you have the picture, it's just like, okay, I'm just looking for a jump discontinuity, something where from the left side it goes to one value, from the right side it goes to a different value. That's all there is. Cool. Okay. You guys ready to move forward?
Oh, question.
Yeah, sure, Elena.
35.
35. Okay. So says determine the infinite limit as the direction. I would do this graphically or tabularly. It probably doesn't really matter. Let's start with the graph though. So we have x times cosecant x. Now I don't have a cosecant x button on my calculator, but it's 1 over sine, so that's what I'm going to type in instead. And we're looking at approaching -2 pi, or I'm sorry, 2 pi from the left. So I'm going to set my own window here, I think. I'm going to go from like 0 to 4 pi. And I'm going to go by pi's or something. And then just go from like -4 to 4 is probably sufficient. So I'm going to start just with this window to get a look at what's going on. So this is 2 pi right here. Okay. I don't think I got big enough here. Let's make this 10s maybe. There we go. So the side I'm looking at is this side, right? So 2 pi is like, there's my cursor heading towards 2 pi, which is right here. 2 pi is like 6.28-ish. So I'm just going to look at those x values and see what's happening. Heading down towards, seems like -infinity to me, right? So you can just write -infinity, and as soon as I pass 6.28, Notice it jumps up to positive values. So that's what I'm looking like it's going on. I'm just going to say equals negative infinity.
That's what I did, but it felt too simple.
No, it's good. Isabel?
Can you do 41?
Sure. Yeah, of course. You're welcome. Estimate the value of the limit as x approaches 0 of 1 plus x to the 1 over x to 5 decimal places. Does this number look familiar? Okay. So we'll start. I'm just going to start by typing this into my calculator. And then I'm just going to use the vars, y-vars function, y1. And I'm just going to be going towards 0. So maybe we start at 1. Okay. And we go to 0.1. So I'm convinced that 1's place is correct because it's still at 2. And then we'll go to 0.01. And okay. And then I'll go to 0.01. And here I'm convinced the 7 is correct. And I'm just going to kind of keep doing this until like the decimal places start constanting out. So like now I'm convinced 7.1 is correct. Are you good with what I'm doing here, Isabel? Okay. So I just do this for a while. You get the idea. At this point, I'm recognizing this number, hopefully. If you don't, this is E. Right? So that's what you should be recognizing. And graphing this thing, if you look at the, as x approaches 0, it should be at the same value there. So let's just some standard. So if I look at this value here, if I zoom in on that, that's right around 2.7 or whatever.
With that graphic, should we plug in a number for x?
No.
Stop it at
Yeah. Isabel, does that feel okay?
Yeah.
Okay. So again, like everything here in this first section was real numeric, real graphical. We're just kind of using intuition. There's not a lot of calculation going on. It's mostly just like getting comfortable with these ideas and what these notations are kind of asking us for and how to think about it the right way. But there's not a lot of like algebra or symbol pushing kind of involved. It's real conceptual at this point, right? That's going to change here as we transition into section 2.3, because what eventually we'd like to be able to do is not have to rely on our graphing calculator to do these limits. We'd like to be able to do them algebraically, ideally with no calculator at all, right? So that's what we're going to start building towards here in section 2.3. So we're going to just start by stating a few properties for limits here. So what this says is if I have the sum of two functions and I take the limit, that's going to be the same as the sum of the limit of the first function plus the limit of the second function. If I have the difference of two functions and I take the limit, zoom in.
Yeah.
Sure.
Thank you.
Sure. If I have the difference of two limits, or I'm sorry, difference of two functions, and I take the limit, that's going to be the same as the difference of the two limits, right? Take the limit of the first function and subtract from it the limit of the second function. If I have a constant times a function, and I take the limit of that, I can pull that constant out front and just do the constant times the limit of the function. If I have the product of two functions and I take the limit, that's the same thing as the product of the two limits. So I can take the limit of one function and multiply it to the limit of the other function. And the same thing with division. If I have the quotient of two functions and I take the limit, that's the same thing as the limit of the first function divided by the limit of the second function. So this just gives us a set of tools that we can use to kind of take a complicated limit and break it up into simpler parts, right? So like, for example, if I had like the limit of like some polynomial, you could write that as the limit as x approaches a of x squared plus 5 times the limit as x approaches a of x minus the limit as x approaches a of 3. Brayden?
For these, do they both be approaching the same a?
Yes. Yeah. So it's like this limit sign is just getting distributed, right? That's all it's basically doing. That's all we're basically saying. Is it just works like you'd hope it would, right? Everything works like you'd hope. And you don't need, notice that we don't need any specific conditions here, right? Like f and g don't have to behave a certain kind of way to be able to do these things. Like you can just do these things. It's okay. So let's look at a kind of a numeric example. So here we have a graph, and I have two functions graphed. F is the pink graph, and g is the blue one. So if I want to do the limit as x approaches -2 of the function f of x plus 5g of x, I can use my properties of limits to kind of break it up like that, correct? Everybody's okay with what I did there? Now I can go to my graph. If I look at -2, which is right here, the limit as x approaches -2 of f of x appears to be that value. Does everybody agree there? And that value appears to be about oh my goodness, I'm looking at the wrong, that's -1, you dum-dum. No wonder, I was like, that's a weird thing. I wasn't expecting that. Okay, we're going here and here. That appears to be approaching 1, right? Everybody agree? Does it matter that it's an open circle it's approaching? No. Okay. And then if I look at the same thing, -2 for g, that's here, and that's up going towards oh, is that because it's 1 right here, right? That's the y coordinate. So this is 0 right here. So g would be -1. So I have 1 minus, or 1 plus 5 times -1, or -4. Let's do another, right? If that wasn't super clear, let's do it again. So again, my limit rules allow me to rewrite this as the product of the two limits. If I find 1 for x, that's here. So the limit as x approaches 1 of f of x appears to be that, which is just the number 2. If I go down and look at the g of x, well, what do I notice here? What's the limit as x approaches 1 of g of x? Doesn't exist because the left-hand limit goes to -2 and the right-hand limit goes to -1. So does not exist times 2 is just does not exist, still doesn't exist, right? Are we doing okay?
Yes.
Is this, again, if you need me to slow down or explain more, or if you're missing something, holler at me. But I'm just trying to read the limits from the graph. So again, I'm going to apply my limit rules or properties. I forget what we called them up there. Is it limit laws? Okay. So I'll do that. And then I'll erase that stuff out of there. Make space. So 2 is right here. So at 2, we're going from the left and the right, we're appearing to head towards that value, right? I don't know, 1.5 maybe? I'm going to put a squiggly because I had to estimate that. It didn't land on a grid line. 1.4, 1.2, or 1.5, 1.6. Like, if you're ballpark, you're fine. It's right around half. And if I look at G, I get 0, right? Well, hold on. So, is this valid what we did? No. So, this would be like kind of a problem. What do I do with this, right? Well, we're gonna get there. There are ways to deal with this, but for right now, we're gonna ignore it and just kind of keep moving forward. But we'll circle back and get to this. Okay? But I just want to put one in here where it's like, be careful, because it's tempting to write like an answer here when really we don't have a way to answer this question yet. Right? Maybe it has an answer, maybe it doesn't. We don't know yet. Because the property that we wanted to use, we actually couldn't, right? So we don't have a way to do this yet, but that's okay. So adding to our limit laws, if I have the limit of f of x to the n, that's the same thing as the limit of f of x raised to the n. So it's like saying this. Basically, we're just saying that you can do something like that. So I can just take the limit as x approaches a of x, get that answer, and then square it, right? Okay. Our next 2 says the limit as x approaches a of a constant is just equal to that constant. Is that surprising? What's the graph of y equals c look like? Just a horizontal line at C, right? As x approaches any value, what is the y heading to? Always C, right? Because it's just the constant, just a straight horizontal line, right? Doesn't matter the value of A. The y is always going to be C. 8 says the limit as x approaches A of x is always going to be A, which again hopefully makes sense if you think about what's the graph of y equals x look like. A diagonal, the coordinates on it are like 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. So the x coordinate is just going to give you the y coordinate out of this. So as x approaches A, y should approach A, because that's what the graph of y equals x looks like. Does that track? Okay. So if I combine properties 8 and 6, I can get to property 9. So let's just to kind of fill that in. We can do this using property 6 and then using property 8. We know the limit as x approaches A of x is just A. So we just have A to the n. That's like our proof. Okay, so that number 9 should not be as a shocking result. So if I look at 10, 10 is the same as 9. How would I prove that? I can prove 10 just using 9. Does anybody remember how to, or think of how to do that? Ugh, come on. What's up? How to prove number 10 just by using property 9? Yeah, except it's 1 over n power. And then if we just use property 9, because 1 over n is just an exponent, right? Whoa! And just knowing to use them is fine. There'll be stuff that you'll have to prove, but I will tell you and do specific examples of that kind of stuff. But they'll be using theorems rather than just like proving an obscure property. It'll be like, this is a problem where I ask you to prove a result using and you'll have to use a theorem. And then we have 5 or 6 of those that you'll have to like end up being memorized throughout the course of the course. But this stuff, like these little properties of how you can manipulate limits, like this is stuff you have to memorize, but you wouldn't have to prove. Right? So just stuff you'd have to use, you have to know. And then similarly, 11, again, I can prove using 6 and whatever. It's the same idea, right, as number 10 was. It just, instead of an x, we have an f of x, which is fine. Notice we have this little assumption. Why do we need that? If n is even, means you have like a square root or a 4th root or 6th root or whatever. Can you do any of those operations to a negative value? No, right? That's why that condition is there. We're just going to assume that the input in your radical, if you have an even radical, is something you can actually do So it's just not like, oh yeah, the whole thing is undefined. All right. So here in our next example, it says evaluate the following limit and justify each step. So let's just do one of these because quite frankly, I don't think I want to do both of them because it's like a lot of step writing. And we're only going to ask you to do this like a couple of times before you can just shortcut to wherever you want. So I would start by using property 1 and property 2. So I can write this as, oops, that's a 5 down there. And then we'll use property 3 to pull the coefficients out front. And then I'll use, which one was that? I'll use property 9. Oops. Come on, there we go. So I have 2 times, and then I'd have 5 squared. And well, let's just do them all here. We did property 9 to do that. And then I'm going to do property 8, and then property 7. So I use property 8 to say this, and then property 7 to say that, and then it just crunch some numbers and we're done. Does everybody feel okay as to kind of like how I step through the properties there? Now here's the reason why I'm not going to make a big deal about this, is because if I look at the next theorem or the next property, this saves us a whole load. Yes, Elena.
Looking at just getting the limit as x approaches 5 at the back equals, or do we just put?
I'm sorry, say one more time for me.
We have to put like the limit notation, like limit of f(x) equals whatever that number is.
So that's why I have like just the equal signs going down.
So you just leave it.
Yeah. So this is just like a train of equal signs, right? Like each step above it is equal to the step below it. You know what I'm saying?
Yeah.
Jacob?
The x is equation 5. I don't get why we can't just like skip to the last one and just plug in 5 for x.
Well, that's what the next property is going to say.
Oh.
Right? So that's the observation, right? Is that, hey, this looks like all I did was plug in 5 for x. And that's exactly what our next property is saying. That says if f is a polynomial or a rational function and a is in the domain, then the limit as x approaches a of f of x is just a, f of a. So a couple things to point out. F in right now needs to be a polynomial or a rational function. What's the domain of any polynomial? All real numbers. So this will work for any value of a for a polynomial, right? Because any a is always in the domain. How about for a rational function? What's the domain of a rational function? All real numbers except where the denominator is equal to 0, right? So here, if you're trying to do this for a rational function, you need to stop and check, does the value I'm about to plug in make a 0 denominator? And if it does, this tool you cannot use. You have to do something different. We'll talk about what other tools we might have here in a few minutes. Is everybody cool with that? So this is pretty specific, right? F needs to be a polynomial or a rational function to be able to do this. But that's what happens. So look at example 3. Is 1 in the domain of our rational function here? No, why not? Makes a 0 denominator, right? So just as, for instance, if I tried to go ahead and use this, I get 0 over 0. This guy is called an indeterminate form. There's actually 6 indeterminate forms, which I've listed below. 0 over 0, 0 times infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, and infinity to the 0. These are things that do not mean undefined. They literally mean you can't say anything about the limit, because you could almost make the limit equal any value you want it to. If you're like if you want to be careful about, you could say 0 over 0 equals 7. You could make it equal 6. You can make it equal 5. It just doesn't tell you anything. So we need a different method to go about doing this. So what is our different trick going to be if we run into something like this? Isabel?
Can't we factor the top?
Yeah, so we'd have to do some kind of algebra. So Isabel correctly identifies that numerator is a difference of 2 squares, so that we can factor. I notice that I have a common factor of x minus 1 in the numerator and denominator. And if I reduce those, I have this and that I definitely can do direct substitution with. And I get the limit is 2. So again, if you run into 0 over 0, that doesn't mean stop. That doesn't mean you're done. It means we have to try something else. And we'll look at some more of these kind of algebraic kind of tricks. Factoring and reducing is just one of them. There's a bunch.
How do you get the 1 plus 1 then?
I did direct substitution. I plugged the 1 in for x.
Oh, okay.
That's the one from third.
Oh.
Yep, exactly. Exactly right. Yes. I just used the direct substitution property listed above. Because now I had a polynomial that I'm taking the limit of, and that I can plug anything into. Okay. So the next little property here says if g of x or f of x equals g of x when x is not equal to a, then the limit as x approaches a of each of them are equal, provided the limit exists. Which is exactly what we used right here, right? Because x plus 1 is equal to x squared minus 1 over x minus 1, except at the value x equals 1, right? But this property below says that's okay. You can still do the limit there. They're just going to be the same. Is everybody good? So all this property is saying when you do this reducing and you'd have like a restricted value, don't worry about the restricted value. Just go ahead and do your direct substitution as you want, which is lovely. Everybody's good? Okay. let's do some more examples. So again, we're doing some limits algebraically. What is this one going to be? The limit as x approaches 1 of g of x, where g of x is the piecewise function x plus 1 for x not equal to 1, and pi, where x equals 1. What do we think? Read the property above. If f of x is equal to g of x, except where x is equal to a, that's exactly what we stating here, right? G of x is equal to x plus 1 everywhere except at 1, right? That's the conditions here. Then I can just say that the two limits are the same. And that I can just use direct substitution on. Get 2.
Oh, so you disregard the bottom one?
Yeah.
Why not x approach 1? Why not plug in
Well,
x?
the alternative here, if you're having troubles looking at it just purely algebraically, let's look at it, the graph of this then, right? So x plus 1 is the line, right, as slope 1. So just kind of like, looks like this. But at x equals 1, it's open circle, and then there it's going to be pi, right? If I look at the limit as x approaches 1, we're just heading to the value 2, aren't we? That's exactly what this property says. If you're doing the limit, that's what it's saying. Right? The limit of the function where you can't plug it in is equal to the limit of a function where you can, as long as the only difference between those functions is the single point that you can't plug in. Right? If everything else is equal, then it's fine. The one little discontinuity there does not matter to us if we're doing limits. Does that feel okay?
Yes.
Okay. All right, let's take a look at this next example. Can we do direct substitution on this? That's probably our first shot, right?
Yes.
What do we get if we do direct substitution?
Wait, we can't.
We get 0 over 0, right? I'd get 3 plus 0, which is 3 squared, that's 9. 9 minus 9 is 0 over 0. Oh, no. Okay, so what should we do then? Yeah, let's FOIL that numerator out. That's a great first step. What do I get when I FOIL out 3 plus h squared? Yeah, whatever order you wanted to write it. I wrote it this way because the 3 was first before. I don't know why. Everybody's good? What do you notice? Okay. What can we do now that the 9s are out of there? Factor out an h. Cancel the h out. And now we're in a spot where we can direct substitute. And we're done. And again, the reason we can do this is that property above, right? Those two things are equal except where h is equal to 0, but it's okay. If we're doing limits, we can just set them equal to each other and continue doing the limit.
If we get 0 to 0, you want us to write like indeterminate form?
No, you don't need to. I mean, you can if you want to. I think it's good for yourself to look at it and go, oh yeah, if I get this, I don't stop. I have to keep going. Everybody's so far so good? Let's look at the next one. Ooh. Okay, if I try direct substitution, what do I get? 0 over 0. Ruh-roh raggy. What should I do? Ah, yuck. Do you really want to FOIL out t squared plus 9 minus 3 times the square root of t squared plus 9 minus 3, or minus 3? Am I still going to get a square root of t squared plus 9 in there? And you can't really square like the top and bottom of a fraction. Like that's not, like that doesn't keep it the same. You could multiply the top and bottom by square root t squared plus 9 minus 3, square root of t squared plus 9 minus 3. But that's not going to solve your problems. Right. Square roots are not distributive.
Well, no, but I'm saying we couldn't just like solve it, like put it as like t plus 3.
That's not, they're not equal. So if I had t plus 9 squared, square rooted, that is just t plus 9. But like t squared plus 9 is not equal to the square root of t squared plus the square root of 9 squared. This is very bad. That's something that's very wrong. Certainly okay to suggest it. Everybody every year suggests this, and everybody gets caught doing this every once in a while, making that mistake. It's very easy to do because you really want it to be true. It makes life so much easier if it is. Here's the trick. Nope. Yes, that's right. We're going to multiply by the conjugate. What do you mean by conjugate? Mr. Kulik, what in the world is this going to solve? Well, what do you get when you multiply a number and its conjugate together? Well, not 1. If I write it this way, I think everybody will know the answer. A minus B times A plus B. Right? It's a difference of 2 squares? Yes? So when I do that, what am I going to get? Well, my A is the square root of t squared plus 9, and then I have the squared on it. And my B is 3. Oops. I'm going to pause here. Are we confused on what I did? So I'm saying that this is like my A, and this is like my B, right? So I just have then a squared minus b squared, right? So I skipped over all the foiling because it sucks, and I already know what the answer is supposed to be. It's supposed to be a squared minus b squared. Is everybody okay with the skip over that I did there? Here's the great part. Squared cancels the square root. So I'm going to have t squared plus 9 minus 9. Yes. Those guys cancel each other out. The t squareds can then reduce. Oops. Can't forget that limit. And now direct substitution is possible because no longer do I get 0 over 0. Yay!
I didn't realize it was calculated.
Yes. It's okay. I'll do that. That's a toughie, right?
Yeah.
But once you've seen it, you'll see it, right? Like the tricks are tricky, but like once you've seen the trick, they're relatively easier to identify. I'm going to stop here right now because I don't want to, this other stuff, I want to be able to go through carefully. So I have the problem set for 2, 3 or whatever. And let's look here real quick. Actually, let's just do this, right? Oops, that's not what I wanted it to do. How about that? I'm just going to do this. So we'll have the 37 comes from something that we haven't talked about yet. So I'm going to take that one off and I'm going to add a new one in. How's that sound?
Really nice.
Yeah. You're welcome. We'll do. We're going to do 26. So I'm going to replace it with that one. Deal? So again, Thursday, we'll do the homework quiz again to start. Same kind of setup. The homework questions that the quiz is on are stuff that we've covered. If you've gotten to the 36 on, you run into some stuff, it's like, I don't know what the heck this is talking about anymore, just stop. There's still a little bit more that we have to do in this section. That's okay. We'll hit that next time. This one, will be a lot of questions from the homework because some of the algebra gets pretty sneaky. So, be patient with yourself. Go slow. Be careful with your algebra, especially for like the stuff that we talked about there a moment ago when you take the square root, that it's not distributive. Like making sure you FOIL things out correctly. You know, keeping in mind those little hints, like making common denominators, like basic algebra things that are easy to fade on. But this feels like a good stopping point before running into the next ideas in this section. There's a big one here at the end that I don't want to just rush through because it's a theorem that we'll have to remember. So it's like a memorization theorem. I want to spend a real time talking about it. Everybody feel okay? I think this works out well because this will probably be a lot of questions from this homework set. And then 2.4 is a survey chapter. It's a chapter with no homework. We're just going to do a couple examples from it, move on. So that probably makes sense for Thursday to go with the homework quiz, the rest of 2.3 and the questions from 2.3 for something that's like, you know, like this is what I wrote for the notes. That's it. There's a lot more to that section, but that's all I wanted to talk about from it. What do you guys think?
Perfect.
All right.